Welcome to the Power System Analysis Control System Part Sheet 5 revision. In this video we are going to discuss about the closed loop transfer function, steady state error, route service criteria, and stability evaluation of the constant K for the stability control of a system. Basic problems which we have studied in your automatic control systems, we are going to review this. To start with, coming to the first problem, we are having a system, closed loop system, and for which we need to evaluate the closed loop transfer function, steady state error due to impulse input, unit step input, and unit ramp input. If you go to the solution, 10 by 100, this is the closed loop system. We are having a inner loop and an external loop. First we will evaluate the inner loop transfer function. Inner loop closed loop transfer function can be written as, we are having a unity feedback, so g of s, h of s is 1, so g of s divided by 1 plus g of s into h of s, 10 divided by 1 plus g of s into h of s, which is equal to 10 by 11. This forms your closed loop transfer function for this inner block. Coming to the outer block, let us change this, we will remove this and change this with this 10 by 11. Now we are having an unity feedback. For this unity feedback, 10 by 11 into this transfer function, we need to combine this and will form a single block as in 1000 divided by 11s into s plus 1 s plus 10. Now we are having a g of s function and then a unity feedback. For this closed loop transfer function will be equal to c of s divided by r of s is equal to g of s into 1 plus g of s into h of s. G of s is 1000 divided by 11s into s plus 1 into s plus 10, and h of s is equal to 1. Just substitute it, you will get it as closed loop transfer function c of s by h of s is equal to g of s value divided by 1 plus g of s into h of s. If you simplify this, you will get it as c of s divided by r of s is equal to 1000 divided by 11s into s plus 1 into s plus 10 plus 1000. This forms your closed loop transfer function. Coming to the second part of the first question, we are having steady state error. We need to evaluate the steady state error for a given input signals. What are the input signals? The first input signal is impulse. How is the steady state error evaluated? Steady state error is evaluated by L of t, s tends to 0. For s into r of s divided by 1 plus g of s into h of s, where r of s is the input signal, and for an impulse input the r of s value is equal to 1. Substitute in place of r of s, we will substitute 1 for this input signal, impulse input, s into 1 divided by 1 plus g of s into h of s. Where we got this g of s? G of s is evaluated from this function. This part is your g of s, and h of s is equal to 1 we know. Simply s into r of s input signal divided by 1 plus g of s into h of s is 1. You will get it as limit s tends to 0, L11 L square. See this denominator, multiply it here, you will get this equation divided by this part. From this you are getting this. Now this denominator part will move to the numerator. You will get it as 11s square s plus 1 s plus 10 divided by 11s into s plus 1 s plus 10 plus 1000. Now substitute the limits. After substitution of the limits, you will get it as 0 divided by 1000. Limits means s is equal to 0. If we substitute 0 here, 0 into anything will become 0. So 0 divided by 0 plus 1000. You will get it as 0 by 1000 is 0. The steady state error is 0 for an impulse input, for the given impulse input. Coming to the second input is, second part of the input. First question is where we need to evaluate the steady state error for a step input. For the step input, r of s which is equal to h by s, where h is equal to 1. Simply you can write it as r of s for steady state, for the step input is 1 by s. steady state error given by S into RFS divided by 1 plus G of S into HFS. The same problem, by input value RFS has been changed to 1 by S. Previously it was 1. Now it has been changed to 1 by S. Substitute the value of 1 by S here. S into 1 by S divided by 1 plus 1000 divided by 11S into S plus 1 into S plus 10 into 1. Limit S tends to 0. Now here, after substitution of 1 by S, S gets cancelled, and this denominator, after multiplication with this 1, this will move towards the numerator. You will get it as 11S into S plus 1 into S plus 10 divided by complete denominator, which is equal to 0 by 1000. After substitution of S here, 0, S is equal to 0, you will get it as 0 divided by 0 plus 1000, which is equal to 0 by 1000. Finally you will get it as 0. Coming for the ramp input, third part is for the ramp input, where ramp input RFS is equal denoted as 1 by S square. ESS is equal to limit S tends to 0, S into RFS into 1 plus G of S into HFS. In place of RFS, we are going to substitute 1 by S square. You will get it as S into 1 by S square as 1 by S divided by 1 plus 1000 divided by 11S into S plus 1 into S plus 10. Now after simplification, we will get it as 1 by S is remaining here, that will be represented here, and this denominator will move towards the numerator and the remaining part will be here. After substitution of the limits, S is equal to 0, it means S is equal to 0 is substituted here, S is equal to 0 is substituted here, and this denominator will become 0, part of the denominator will become 0, which is added to 1000. So it can be written as 11 into 1, this one, into 10, 0 plus 10, 10 divided by 0. This complete part as 0 into this complete all becomes 0 plus 1000. You will get it as 110 divided by 1000, which is equal to 11 by 100. This forms your first question. Coming to the second question, where we need to evaluate the stability of the system by Rausch-Hurwitz criteria. Study the following characteristic equation. We are having an characteristic equation for which we need to evaluate the stability study, whether the system is stable or not. This equation we can represent for Rausch-Hurwitz criteria. Right, we are going to represent the coefficients, see, S power 5, S power 4, S power 3, S square, S power 1 and S power 0. We will write it in the column format, S power 5, S power 4, S cube. For this S power 5, the coefficient is 1 and the alternate, this is an odd number, odd degree coefficient here is, next factor is 5. After this odd degree coefficient is S power 1 is 1, coefficient is 1. Coefficient of S power 5 1, coefficient of S power cube is 5, coefficient of S power coefficient of S power 1 is 1 here. Now the second order is S power 4. For S power 4 coefficient is 4, then alternate term is S square coefficient is 1, and then we have the coefficient as 1, constant as 1. Now we will multiply, cross multiply and divided by this parameter just above this. So 1 into 1, so simply we will start from here, 1, 4 into 5 is 20, minus 1 into 1 is 1, divided by, just above this we are having 4. You will get it as 20 minus 1 by 4, the resultant is 19 by 4. This is not power, this is the solution of this, this is the resultant, this part 19 by 4 is the resultant of this expression, 20 minus 1 by 4 is 19 by 4. And similarly here, 1 into 1, 1, minus 1 into 5 is minus 5, 1 minus 5 divided by 1, you will get it as minus to the power of 4, which is equal to minus 4, 1 minus 5 by 1 minus 4. And here we don't have any expressions, so we cannot move further. 1 into 0, 1 into 0 or something, will get it as 0. Similarly, now for S square, to write this expression we will start from here, 19 by 4 into 1, 19 by 4 into 1 plus minus 4 into 4 minus 16. Here as we are having minus of minus 4 into 4 is minus 16, you will get it as plus 16 divided by just above this. What is the term above this? 19 by 4. Just we will write it here. The resultant of this will be 83 by 19. Then similarly, to write this expression, we will start from here. Minus 4 into 1, minus 4, minus 0 into 1, 0 divided by just above this we are having minus 4 divided by minus 4, and this expression will be 0. Now the resultant of this is 83 by 19. To write this expression s power 1, we will start from here. This into just above 83 by 19 into minus 4, 83 by 19 into 4 into minus 4 minus this parameter 1 into 19 by 4. 1 into 19 by 4 is 19 by 4 minus 19 by 4 divided by just above this is 83 by 19, 83 by 19. Just above this expression what we have, 83 by 19, and the resultant of this is minus 967 divided by 332, and this expression will be 0. If you want to evaluate this expression, this just above this we are having this expression 1 into 0, 0 minus 0 into minus 4 will be 0, 0 minus 0 divided by this value, 0 by 1 is always 0. We get 0, and this parameter will obviously be 0. Now to write this s power 0, we will start from here, from minus 967 divided by 332 into 1, 332 into this 1 minus 0 of 83 by 19 minus 0 you will get divided by just above this minus 967 by 332. So you will get it as minus 967 divided by 332 minus 967 by 332, you will get it as 1. Check this parameter should be equal to this parameter. It means your calculation is right. Now finally, for the stability, what we need to observe, the change of sign. If you check the sign, here it is positive, plus 1 plus 1 plus sign plus sign plus sign plus sign plus sign, and then from positive to negative, one sign change, again from negative to positive another sign change. Total we have 2 sign changes. It means as there are 2 sign changes, there are 2 roots in the right side of the S plane and the system is unstable. If there is no sign change, then the system will be stable. If all are positive, then the system is stable. If all are negative, then the system is stable. Presently, as there are 2 sign changes, there are 2 roots which are in the right hand side of the S plane, and the system is unstable. This part we did it. Now coming to the third question. The third question is we need to find the range of the K. This is extra questions for your practice. I have given it here for Rhodes criteria. This is the third question. We need to find the range of K that keeps the system stable for the following control system. It means we need to calculate the range of K. We don't know the value of the K, but the system is stable. To find the system stable, we need to evaluate the characteristic equation. What is characteristic equation? 1 plus g of s into h of s. This is g of s, h of s is equal to 1. So s into s plus 1 into s plus 10 plus k is equal to 0. This forms your characteristic equation. This 1 plus, if you elaborate this, simply see 1 plus k by s into s plus 1 into 1 is equal to 0. If you elaborate this, you will get this equation. How? Simple, see, you will get it as s into s plus 1 into s plus 10 plus k divided by s into s plus 1 plus s plus 10 is equal to 0, and this denominator it can be moved to this side. Finally you will get it as s into s plus 1 into s plus 10 plus k. Now if you put it in the equation in the Rhodes criteria for the Rhodes Harvest stability format, Rhodes table, we call this as a Rhodes table. Start with this equation. Once we get this equation, the highest degree is cube. So x cube, s square, s power 1 and s power 0. Coefficient of s cube is 1 and the alternate coefficient is 10. So 1, 10, and then we don't have any expression after this. Similarly, go for s square coefficient is 11 and the alternate degree is k. Now let us calculate S1 term. S1 term will be 110 minus k divided by 11. So from 11 into 10, 11 into 10, you will get it as 110 minus k into 1k divided by, just above this expression we are having 11, divide it with 11. And coming to this expression, k is moved this side, k into the value which is present here, nothing is there, so it will be 0. K into 0 minus 0 into 10, it will be 0, divided by, now this expression, now we need to evaluate this expression, s power 0. 110 minus k divided by 11 into k minus 0 into 11 minus 0 divided by this numerator, 110 minus k by 11. You will get it as 110 minus k by 11, 110 minus k by 11 will get cancelled, remaining will be k. The left out parameter is here is k. Here the sign is positive, here the sign is positive, it means this expression should be positive for a stable system. Why? There should not be any sign change. It means if this is positive, we can write it as 110 minus k by 11 is greater than 0. So you can write it as k is less than 110. One expression we got. And for this, k is left out here. It means k should also be positive. When is k positive? K is positive when k is greater than 0. There should not be any sign change for a stable system. Hence we are taking k is greater than 0. This is positive, this is positive, this should be positive. When it is positive, when 110 minus k by 11 is greater than 0, when this is positive, when k is greater than 0. So you can say, by combining this expression, k is less than 110 and k is greater than 0, we can write it as k should be between 0 and 110. For the system to be stable, k should be positive, and means k should be greater than 0, or you can write it as k should be between 0 and 110. With this we have finished the basic review of the control system. In the next session we will discuss about the problems related to low load frequency control and automatic voltage regulator.